Chapter 1, Part 5. Topics covered are electrical properties of solids, band theory, metal, insulator, and semiconductor, and magnetic properties of solids.
Today's topic: electrical properties of solids. The topic we will study is conductor, insulator, semiconductor. All these topics my favorite sir will teach you. Bye!
Conductors. Solids having electrical conductivities in the range 10 raised to 4 to 10 raised to 7 ohm 1
are called conductor.
Metals conduct electricity by movement of electrons, and as you can see, the electrons inside the metal are moving.
Conduct electricity by movement of ions.
Here aqueous solution of electrolyte are called conductor.
Today I will kill you by giving shock.
Hey, I will not get shock. Because Aklesh sir had given me insulator shield, whose conductivity range 10 raised to minus 20 to 10 raised to minus 10 ohm inverse minus 1 the tier inverse minus 1.
This shield is made of insulator, example, non-metal and molecular solids, so I will not get shock.
Today I will explain what a semiconductor is. Semiconductors are solids having electrical conductivities in the range 10 raised to
minus 6 to 10 raised to 4 ohm 1 M1 are semiconductors. This range is intermediate between conductors and insulators. Metals, like silicon, germanium, belong to semiconductor category.
Next topic we will study is band theory. Band theory. Electrical conductivities of solid metals, nonmetals and metalloids are explained in terms of band theory. To understand the basic of band theory, let us take example of magnesium atom. In a single atom such as magnesium, whose atomic number is 12. So its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p0. In magnesium atom, electron of atomic orbital occupy fixed and discrete energy levels, like 1s, 2s, 2p, 3s, and 3p remain vacant. These energy levels are separate and do not overlap with each other. According to molecular orbital theory, interaction of atomic orbitals of combining atoms results in formation of equal number of molecular orbitals, which spread over the entire molecule. To understand above statement, let us take example of two magnesium atoms come close to each other. Their atomic orbitals interact. In molecular orbital theory, we can see each energy level splits into two new energy levels. That is bonding and another anti-bonding. Thus each energy level split into equal number of molecular orbitals. Thus a single system of two atoms consists of many bonding and anti-bonding orbital. Consider a single system of two atoms, which split into two energy level bonding and anti-bonding. So if there is n atom, each individual level split into n energy level. These closely spaced energy levels merge together to form energy bands. The band with lower energy is called the valence band, and the higher energy band is called the conduction band. The region between these two bands is called the energy gap.
types of bands. So here you can see various types of bands are there. Okay, so here first band, second band, last valence shell band. Then there is one more band which is known as condension band. Okay, there are the different energy bands. We will focus on valence band and condension band. So what is valence? The band which has a lower energy than the condension band is the valence band. Always remember, the valence band has a lesser energy as compared to the condension band. Valence band is that band where the electrons in the valence band are not free. Okay, the valence band, the electrons are not free. They are tightly bonded by the respective nucleus. For example, see, this is a magnesium atom, and you know that it has a configuration of 2, 8, 2. So here the last shell, this is the last shell electron. The last shell has 2 electrons. So this 2 electron is tightly bonded by the nucleus of the magnesium. So this is not free. So in valence band, the electrons are not free. Okay. So all these electrons which are present in this band are known as a valence band, because all the atoms, all the magnesium atom last shell electrons are always placed in which band? Valence band. Okay. Now, so they cannot move from that band. Okay, from that shell also you can say. Okay. Now there is a conduction band. What is the meaning of conduction band? Conduction means what? Conduct electricity. Okay. So conduction band may be partially occupied or vacant. Means there may be some free electrons present in the conduction band, or it may be a vacant. It depends on solid to solid. Okay. So electron in the conduction band is what? If any electron, see here, suppose if any electron here, assume that this electron, okay, which is now in the valence band, now maybe for any reason this electron became free. Okay, this electron became free and it is moving. Okay, it was there in the valence band, now it is free. Now this free electron are present in which band? Conduction band. Now see here. Okay, now this electron is present in conduction band. Now suppose same electron which was there in the valence band, now after giving certain energy, this electron will move from to conduction band. Okay, and this electron is free, and this electron is responsible for conducting electricity. Suppose if I give a potential energy, see what is written? Electrical potential. So in this wire there is a conductor. Okay, so what happened when you apply a potential difference? The electron which was present in the valence band, now it became free and it is moving. Okay, and it is conducting electricity. You can see here the electron is moving. So what happened? How the electron get free? When it was tightly bonded by the atoms. Now if you apply the potential difference, the electron will move to the conduction band, move from valence band to the conduction band, and it will conduct electricity. Therefore it is given as name as conduction band. Conduction band electrons are very free and it will conduct electricity. That's why the name is given conduction. Now next, band gap. Okay, let's study about the band gap. Is what? The energy differences between valence band and conduction band, okay, is called as band gap. So here, see here, this is the valence band and above it is a conduction band, and between this valence band and conduction band difference, in between that you can see there is a gap. Okay, and that gap is known as band gap. So to find that band gap, if you want to find that band gap, you should know what is the energy of the valence band electron which is present in the valence band, what is the energy, and what is the energy in the conduction band. Okay, so you know that some amount of energy is required to become free, and that amount of energy which is required for the electron which was in the balance to become free, is that energy is known as band gap. Suppose if I give the this electron, if I give the band energy, okay, that amount of energy which is required to get free, so this electron will get free and it will get moved from valence band to the conduction band. The energy difference between valence band and conduction band is known as band. Now, this band gap, this size determine, see what is written here, size of the band gap decide whether the electron from the valence band can be promoted to vacant conduction band or not. Suppose if the band gap is more, the electron will not get free and it will go to the conduction band. Okay, it depend upon, suppose here the electron has went to the conduction band, and suppose if the band gap was more, what will happen, the electron will not promote to the conduction band and it will return back to the valence band. Okay, so it depend upon the band gap. The solid has divided in we have divided the solid into depending upon their band gap. Okay, so we will next study when the band gap is too large. Suppose if the band gap is too large, for example, this is the valence band, this is the conduction band, and if the conduction band, the gap is more between valence band and the conduction band, this is the band gap which is very too large. Now if you supply the heat also, then also that electron will not get a sufficient amount of energy because the band gap is more, so it will not go to the conduction band and it will remain in the valence band and it will not conduct electricity. So this is known as forbidden zone also. Forbidden means it is not allowing the electron to move to the conduction band. That means it is not, electron is not getting free and it will remain in the valence band because electrons are tightly held by the metal. Okay, so here it is written, when the band gap is too large, it will to promote the electron from the valence band to the conduction band, thermal energy. Thermal, here we are supplying the thermal energy, and the band gap is forbidden zone. Okay, next. Okay, suppose the band gap is very small. So what will I will bring the conduction band to the side. Now the band gap is very small. So what will happen, because since the band gap is very small, the electron, if I supply the thermal energy, electron can easily move to the conduction band. Okay, so because the band gap is small, electron can easily move to the get free, and if it get free means it is in the which band, conduction. Okay, so what is written here, when the band gap is small, the electron from the higher energy level electron can go to the higher level energy from the valence band by promoting to the conduction band by absorbing energy.
The electrical properties of metallic conductors, insulators, and semiconductors are explained in terms of band theory.
In the conductors, the forbidden gap is negligible. Hence the jumping of electrons from valence band to conduction band is easy. Little amount of energy is sufficient to promote the electrons from valence band to conduction band.
Let's study about the metals. In metal, the outermost electron of all the atoms in a metallic crystal occupies a conduction band. Okay, so here you can see there is a this is a metal crystal. There is a positive charge, and this electron is moving under the influence of the potential difference. If you apply positive and negative, the electron is moving. So here there is in the metal, the electrons are free. So outermost electron, this green represent the outermost electron of all the atoms in a metallic crystal occupies conduction band. What is the meaning of conduction band? See here. There is two type of bands are there, valence band and conduction band. Valence band is that band which is present at the last shell of the electrons, the last shell of the atom. Okay, and conduction band is that band where the electrons are free. So what happened? These free electrons are present in the conduction band. So what is the meaning of conduction band? Conduction band is that band which conduct electricity. Now, the number of electrons in the conduction band of the metal is very large. As you can see here, in the metal, electrons, there is a large number of electrons are present in the conduction band. So always remember, in metal, there is a large number of free electrons are present in the conduction band. So the number of electrons in the conduction band of a metal is large. Next. So because the number of electrons in the conduction band is large, the metal is a very good conductor of electricity. Here you can see here in the animation, as this wire, inside the wire it is made up of copper metal. So as soon as you close the circuit, the free electrons moves and the bulb glows. This means that metal is a good conductor of electricity. Electrons can move very easily. Okay, and the bulb glows. Okay, next. Consider one example, metallic sodium, whose electronic configuration is argon 3s1. Here the last shell 3s contain one electron. Okay, so this is one box and there is only one electron. So this is a 3s orbital. Okay, this is 3s orbital which containing one electron. Okay, means it is a half filled electron. Okay, so what is this? This represents the conduction band. Okay, so this how the band has came here. This is known as conduction band. Okay, there are many sodium. This is the one isolated sodium atom. There are a large number of sodium atom are there. All the sodium atom last shell contain one electron. Okay, so all the electrons of the 3s orbital will occupy this space. Okay, so you can see here this 3s orbital is half filled and half empty. Okay, so half filled and half empty. So this part, that all the atoms of the sodium whose 3s electron will be placed here in this band. Okay, so S band is that band. S band, that is bluish part, is that part where all the electrons of all the atom of the sodium atoms is placed here. So rest part is empty because each as sodium atom has half filled and half empty. So total 50% is filled and 50% is empty. Now, so this empty. So this electron can easily move inside this band. Okay, electron can move very easily because there is a space are empty. Okay, next. So next example, magnesium. Magnesium has a 3s electron which is completely filled and the last 3p orbital is empty filled. So here 3s has 2 electron and 3p is empty. Now this is S band. This is S band of what? 3s. Okay, and it is, since it is completely filled, this is fully completed. Okay, there is no empty space in the 3s orbital. Okay, this is completely filled. As you can assume like that, there is one bus which is each seat has two person can sit on this each seat. Okay, and all the seats are covered. Okay, there is no spaces there. All are sitting at each places. Okay, so bus is full. Now, so there is one more bus which is fully empty. Assume that 3p is one bus. Okay, and it is fully empty. Okay, and it is coming from behind. Okay, so this 3s electron will occupy 3s S band, which is completely filled. There is no empty space in it. Okay, now this P band is totally empty. It is coming from behind. Like that, you can assume that there is a one bus which is S band bus which is fully filled, and one P band which is coming from behind which is empty. Now this bus come very near to the S band. Okay, so assume that it is coming very near. So the last seat, some person can move easily to the P band. Okay, and occupy this, and because of that, some part of the S band will be get empty. See, like this. Okay, so slightly the electron from the last part can go to the P band. Okay, so this is the diagram for magnesium. Okay.
Insulators, the forbidden gap is more. Hence the jumping of electrons from valence band to conduction band is not possible.
Insulator. In insulator, the valence band is completely filled with the electron. So assume this is the energy graph. Okay, and this is the valence band which has very lower energy as compared to the conduction band. Okay, and in the insulator, all the electrons are present in the valence band. Okay, and the conduction band is empty. There is no electron present in the conduction band. Okay, for example, if you assume wood, plastic, we never get shock whenever a current is passed, it will not allow the current to pass because there is no free electrons present in the conduction band. All the electrons are tightly bonded by the atom and they are present in the valence band. Okay, so here this conduction band is empty. The band gap between the valence band and the conduction band is very large, so it is very difficult for the electron to move from valence band to the conduction band. So here see, the valence band and the conduction band in the insulator are separated by a very large energy called as forbidden gap. Forbidden means what? It is not, electron cannot be moved to the conduction band easily. Okay, so it is very difficult because the band gap is very large. This electron will require a large amount of energy to move to the conduction band. Okay, now suppose even if you supply the thermal energy is not sufficient to promote the electron to the valence band to the conduction band. Even if you supply the energy, the electron will not move from valence band to the conduction band because the energy is very large to make the electron to free. Okay, next. As a result, the conduction band will always remain empty and this material will behave like an insulator. That is, it will not allow the current to pass because there is no free electrons present in the conduction band. Okay. So this you can see here, the bulb is not glowing because in between you have kept the wood, and wood is a insulator, therefore no electrons are free in the wood, therefore the current will not flow. Next, insulator. Assume this is a filled valence and this is the empty conduction band. Okay, filled means all the electrons are there in the valence band and there is no electron present in the conduction band, and the band gap is very large here, so no electron will be moved from the valence band to conduction band. Now here, example of insulator: glass, plastic, ceramic, any wood, fabric, paper, cork, wood, wool also you can take. Okay, these are all example of insulator where the conduction band are empty.
In the case of semiconductors, the forbidden gap is moderate. Hence, the jumping of electrons from valence band to conduction band is possible when the energy equal to the forbidden gap is supplied.
Now study semiconductor. Okay. So here the electrical conductivity of the semiconductor is intermediate between the metal and the metal and the insulator. So here you can see this is a master of semiconductor. Okay, suppose, and this germanium and silicon is a semiconductor. Okay, if anyone say what is the example of semiconductor, you can give the example of germanium and silicon, and its conductivity is in between. Okay, this is a metallite and this is a semiconductor, and this is their conductivity is intermediate between conductor and the insulator. Okay, like a conductor is not there, not like a insulator is there. It is in intermediate because conductor has large number of free electrons. This do not have that much free electrons. Very less amount of electrons are there. And in some time this silicon can behave like an insulator also. It will not allow any electron to move, so it can behave slightly like a conductor and slightly like an insulator. So there is a you can say that electrical conductivity of semiconductor is between conductor and insulator. Sometimes it behave like a conductor, sometimes it behave like an indicator, depending upon what condition you are giving to the silicon and germanium, that is semiconductor material. Next. The valence band in the semiconductor is completely filled with electrons and the conduction band is empty. Here you can see this is a filled valence band. So all the electrons present in the valence band are fully filled. There is no empty space in it. Okay, and the conduction band is empty. But the what is the difference from the insulator? It is the band gap. Here the band gap you can see as compared to insulator is very less. So here the band gap is very small. Now, however, the energy gap between the two band is very small than that of insulator. Okay, so as compared to insulator, the band gap is very small. Next, semiconductor. At temperature 0 Kelvin, that is in -°C. Okay, semiconductor behave like an insulator. So see here, I told you semi means half. It behaving like half conductor, not fully conductor. Suppose if you give the condition as suppose the temperature is 0 Kelvin, this semiconductor behave like an insulator. 0 Kelvin means minus 273 degree Celsius. So that is called as absolute zero. So at that time, no electrons will move from valence band to the conduction band. Now at temperature above 0 Kelvin, the semiconductor conducts some amount of electricity, means it gets certain amount of energy, and some very few electrons can move from valence band to the conduction band. So above means what? Minus 273 means you have increases slightly temperature. Okay. Then what happened? Some electrons which is present in the valence band will move to the conduction band because it gained a certain energy. Okay. As a temperature above absolute zero, if few electrons in the valence band has enough thermal energy to jump through the small band and occupy the higher energy conduction band. Now suppose if I increase the thermal energy, or you can increase the heat, then some few electrons will get a certain amount of energy and it will move to the conduction band and it will get free, and and the valence band will be empty. Okay, some part of the electron go to the conduction band and became free, and it will conduct electricity. So you can see here, now it is behaving slightly like a conductor. Okay, so depending upon what condition you are giving, it is behaving like an insulator and conductor. If you give the temperature below 0 Kelvin, it will behave like an insulator, and above 0 Kelvin, it will behave like a conductor. Okay, so here it is partially filled. Now it is partially filled here. Okay, next. And partially empty and partially filled. Okay, the valence band is partially empty and the conduction band is partially filled. Now, and this electron which is present in the conduction band are now free to move when the potential difference is applied. So you can see here, when you applied a battery, that is potential difference, some free electrons which was present in the conduction band is moving towards the positive terminal of the battery, and that will conduct electricity. Okay. So that is given here. So some few electrons may present in the semiconductor. Okay. Such a pure semiconductor material which has very low but finite electrical conductivity is known as intrinsic semiconductor. Such type of semiconductor which has a very low conductivity, it is behaving slightly like a conductor because of very few electrons present in the conduction. So such type of semiconductor is known as intrinsic semiconductor. Now, at temperature, so you can assume that, or you can say that, you can make a conclusion that as the temperature increases, semiconductor electrical conductivity increases. So as the temperature increases, more and more electrons get free. So number of electrons with sufficient energy so as to get to promote to the conduction band. So if you increase more and more temperature, if you increase the temperature, see, if a temperature is given, electrons get free. There is a partially filled electron present in the conduction band and partially get empty. Now if you supply more amount of heat, then more number of electron get free and it move to the conduction band. So as the temperature increases, the electrical conductivity increases because the number of free electrons increases. Now, thus at high temperature there are more mobile electrons in the conduction band, and more vacancy is created in the valence band at high temperature. So at high temperature vacancy is created and a large number of mobile electrons are created in the conduction band. So semiconductors are insulated at what? Low temperature and behaving like a conductor at very high temperature. Now what is extrinsic conductor? Now before that we have studied the intrinsic, that is pure semiconductor. There is no only silicon or only germanium was present. Okay. Now here extrinsic semiconductor. Here you can see this is the intrinsic semiconductor. There is all are silicon, all are made up of silicon. There is no other elements present. Here this dot represent the electrons of the outermost shell electrons. See here you can see this silicon. Silicon is surrounded by a silicon has 4 electrons in the valence band. Okay, and it is sharing 1 electron with the neighboring silicon atom. So total there is 8 electrons are surrounded by the 1 silicon atom. Okay, Now there is no free electrons present in it. Now what I will do, I will increase the conductivity of the semiconductor, and that process is known as doping. So how to increase the conductivity of this intrinsic semiconductor? To increase that, suppose if I take the impurities like lead, Pb, which is known as donor impurities, what I will do, I will add this lead in the semiconductor. Okay, when I add this impurities in this pure semiconductor, that is intrinsic semiconductor, that process is known as doping. The addition of any impurities atom to the semiconductor is known as what? Doping. Now, so this impurities, when added to the semiconductor, what it will do, when you add this impurities in this semiconductor, it will increase the conductivity. This impurities is added here. Now it will increase the conductivity. How it will increase? It will bring more number of free electrons. Okay, so you can see there is a one extra, this conductivity has increased, and it has brought a extra electron, and this extra electron will be present in the conduction band. So as the impurities increases, extra electrons in the conduction band also increases. So if the number of electrons in the conduction band increases, the conductivity increases. And this which we have added, the impurities, is known as dopant. So impurities which is added is known as dopant, which has increased the conductivity of the intrinsic semiconductor. Now it is not a intrinsic semiconductor, it is now called as extrinsic semiconductor. What is mean extrinsic? Extrinsic means what? Externally you have added some impurities and to increase the conductivity. So now this semiconductor is known as extrinsic semiconductor. Okay, so a doped semiconductor means what? Addition of impurities to the semiconductor have increases what? Conductivity. So you can see here the doped semiconductor has increases the conductivity of what? Pure intrinsic semiconductor, and such type of semiconductor is known as extrinsic semiconductor. Okay, there are two type of extrinsic semiconductor. One is p-type semiconductor, another is n-type semiconductor. In p-type semiconductor is produced by doping a pure semiconductor material such as silicon or germanium with the impurities of group 13 element. So what we will going to do here, we will take a pure semiconductor material, and in that we will add impurities, and that impurities atom has contained 3 electron in the outermost shell, and it is belonging to the group 13 element. Element which is belonging to the group 13 element has last shell contain 3 electrons. So if you add a group 13 element to a pure semiconductor, that pure semiconductor will become a p-type semiconductor. Now here n-type semiconductor is obtained by doping a pure semiconductor like silicon and germanium with the impurities of group 15 element. So in this what you will going to do, you will going to add the impurities of group 15 element which has last shell containing 5 electrons. Okay, so we will see one by one in detail. Okay, so first we will study about p-type semiconductor. A p-type semiconductor is produced by doping a pure semiconductor material with the impurities of group 13 elements. So here this is a silicon crystal. Here you can see the silicon is surrounded by 8 electrons. This orange one is this silicon electrons, and this black one is the neighboring electrons of the silicon atom. Okay, now it is a pure semiconductor because there is no another impurities is added here. Now suppose if I remove one silicon atom. Okay, so now group 13 element, which example boron. Boron last shell contain 3 electrons and it is belonging to the group 13. Now what I will do, I will add this impurities, that is dopant. You can say dopant. Dopant means the impurities which is added is known as dopant. So here the dopant which is added contain 3 electrons. So boron has 3 electrons is shared by 3 silicon atom, but one part is you can say there is no electron, 4th electron present in the boron. So that part remain empty, and this is known as hole. Now you can make the simplified same diagram is there here also. Boron you can see 1, 2, 3, 4, 5, 6, 7, and one is, since the boron has deficient of 1 electron, therefore it is not sharing its own 1 electron to the silicon. So that part remain vacant. 1, 2, 3. 3 is shared by silicon and 1 is remaining empty. And that empty part is known as hole. And such type of semiconductor is known as p-type semiconductor. Why the name is given as a p-type semiconductor? P means positive. Here the hole is considered as positive charge. That's why this whole semiconductor is known as p-type semiconductor. Now, p-type semiconductor. So you can say that in the valence band, most of the valence band contain electrons, but some part, as the impurities is added, some part of the valence band is empty now, and already the conduction band there is no electron, so this will be remain. Okay, now in p-type semiconductor, hole, that small part empty space is nothing but the hole which is created by that impurities. Okay, so as the impurities is added, this white part will go on increasing. Okay, and now in this p-type semiconductor, hole is in the valence band. Okay, the electron in the partially filled valence band move under the influence of applied field. So this is a silicon atom, this is a boron impurities which I have added, and if I apply a potential difference, suppose if I use a potential difference by using a battery, what will happen? So here this is empty field which is known as hole. The hole has a tendency to accept the electron. Since the hole is considered as a positive charge, so under the influence of the potential difference, this hole will going to attract the electron from the neighboring silicon atom. So the hole has a tendency to accept the electron in the close vicinity, means nearby. Does the hole behave like as if is it a positive charge? So what will happen due to the under the influence of potential? This electron will going to move from, see this electron is moving to the empty filled part. Okay, that is positive holes, and this electron, another electron will share that hole. So now the hole is created in this side. Okay, so in this way, now the hole is here. The hole is moving in the opposite direction where the electron is moving. Electron, suppose if I assume that electron is moving is left hand direction, hole is moving on the right direction. The hole's direction is opposite to the electron motion direction. So you can assume that because of the charge carrier, what is the charge carrier here? Here electron, that is hole, which behave like a positive charge. The silicon and germanium which is doped with group 13 element, like which all impurities you can add, just like boron, gallium, indium, all are group 13 elements. If you add in the pure semiconductor, that semiconductor will become as a p-type semiconductor. Now n-type semiconductor. N-type semiconductor is produced by doping a pure semiconductor like silicon and germanium with the impurities of group 15 element. So here this is an intrinsic semiconductor, pure intrinsic semiconductor. There is no dopant, no impurities is added. Now what I will do, I will remove this silicon atom and I will add the impurities, that is phosphorus, which is belonging to the group 15 element. Is if you can see here, the last shell contain 5 electrons, 1, 2, 3, 4, 5. So if I add this impurities in the silicon atom, that is intrinsic semiconductor, out of the 5 electron, 4 electron will be shared by the neighboring 4 silicon atom, and 1 electron will not share by any electron, and this electron will be free. Okay, and these free electrons, this mobile electrons, will go to the conduction band. Okay, now because of this free electrons, here same diagram, see here. Okay, here out of 4 of the 5 valence electrons. So out of 5, 4 of the valence electron are utilized in bonding. Okay, you can see here is utilized in the bonding. The green part of the phosphorus is shared by 4 silicon. The 4 is used and 1 electron is empty. Oh, sorry, 1 electron is not shared. Okay, so this extra electron is not shared, it has not formed the bond. And such type of semiconductor is known as n-type semiconductor. Why it is called the n-type? Because n means negative charge, and this electron is responsible for conducting electricity. So this electron will be in the conduction band, and this free electron is responsible for to increase the conductivity of n-type semiconductor. Now this n-type semiconductor, already the electrons are filled in the valence band, and now Now there are some electrons which are present in the conduction band. Now it is not empty because some electrons, because addition of impurities has increases the number of electron in the conduction. So some part of the conduction band has containing a free electrons. So okay, this is extra electron. The silicon when doped with phosphorus has more number of electrons in the conduction band than the conduction band in pure semiconductor. In pure semiconductor, there is a conduction band was already empty. Now when you add the phosphorus, that is pentavalent impurities, some part of the some free electrons get occupied at the conduction band. So when the electron in the conduction band is moved under the influence of potential difference. So this is a extrinsic semiconductor, that is N-type semiconductor. Now I will apply a potential difference by using a battery. So what will happen? These free electrons will going to move under the influence of this potential difference. So this electron is moving towards the positive terminal of the band. So you can assume that here the conductivity of the N-type semiconductor has increased because of this free charge, that is free electron charge. So because of the charge carrier has increased, that is electron has been increased, number of electrons, the silicon and germanium which is doped with group 15 element like phosphorus, arsenic, antimony, bismuth is a N-type semiconductor.
Today's topic. Magnetic properties of solids.
I am a magneto man. Today topic name is magnetic properties of solid.
Magnetic properties of solids? Magnetic properties of solids can be understood easily in terms of classical picture of electron. The electrons spin about their own axis.
The spinning electrons act like tiny magnets because their spinning action generates induced magnetic field.
Magnetic properties of solid. When an orbital has only one electron, its spin is unpaired or unbalanced. Because of this unpaired spin, the electron behaves like a tiny magnet. Therefore, the solid shows magnetic properties. In simple words, if electrons are not paired, they create magnetism. When electrons are paired, their spin is balanced and no magnetic property is observed.
1. Diamagnetic solids. The substances with all electrons paired in diamagnetic solid, all atom present inside it contain paired electrons, are weakly repelled by magnetic fields. Suppose a magnet is brought near the diamagnetic substance. Diamagnetic substance get weakly repelled by magnetic field. These substances are said to be diamagnetic.
Take a piece of foam with a hole in the middle. This is a small test tube, transparent, and test tube is stand vertically in this foam. Due to this hole, pour water in the test tube and kept slowly on the surface of water so that it can float on the surface of water. Take a powerful neodymium magnet. Just bring the magnet near the test tube filled with water. As you can see, the test tube containing water is slowly moving away from the magnet. Since water and glass is diamagnetic substance, it will weakly repelled by the magnet. If I bring magnet from other side, test tube is again moving away from magnetic field. This proved that water and glass is a diamagnetic substances. Inside diamagnetic solids, the atoms contain paired electrons, which has an orbital motion and also has a spin motion. Each electron spins around its own axis, and due to this spin motion, a magnetic field is produced. Here you can see due to spin electron is producing magnetic field. But since the electrons are paired, they spin in opposite directions. Therefore, the magnetic moments produced by the two electrons are also opposite in direction. These opposite magnetic moments cancel each other. so the atom has zero net magnetic moment.
Let us consider helium atom, which contains only one pair of electrons. The paired electrons have orbital motion and spin opposite to each other. Due to this, the pairing of electrons balances the spins, and the net magnetic moment are opposite to each other, and hence cancels their magnetic moments.
I am diamagnetic by repelling all molecules around it.
Examples of diamagnetic substances are nitrogen, fluorine, sodium chloride, water, and benzene.
2. Paramagnetic solids. The substances with has unpaired electron. Here this is substance, which has many atom, where each atom contain unpaired electron, are weakly attracted by magnetic fields. Let's see what will happen if magnetic field is applied around paramagnetic substance. Because paramagnetic substance contain unpaired electrons, these substances are weakly attracted when placed near a magnetic field. These substances are said to be paramagnetic. Inside paramagnetic solids, atoms contain unpaired electrons. These unpaired electrons has orbital motion and also spin motion around the nucleus. Because of this spin motion, each electron behaves like a tiny magnet and produces its own magnetic field. This creates a magnetic moment for each atom. Thus spin motion of electron produce magnetic field, which result in magnetic moment. Thus paramagnetic solid shows net magnetic moment.
I am paramagnetic substance attracting man. I had power to weakly attract the paramagnetic substance.
Definition of paramagnetic solids. The substances with unpaired electrons are weakly attracted by magnetic field. These substances are called paramagnetic substances.
Paramagnetic substance has unpaired electron, which is spinning about its own axis. It gives rise to a magnetic moment.
Because I can produce magnet moment in paramagnetic substance. These substances exhibit magnetism in presence of external magnetism only.
They lose magnetism when the external magnetic field is removed.
The examples of paramagnetic substances are oxygen, copper ion, Fe+3, and chromium+3.
I am Pharaoh. Wait, I call my hammer Aklesh hammer. Today topic, ferromagnetic solid. Ferromagnetism. Substances
containing large number of unpaired electrons. And this
substances attracted strongly by magnetic field are ferromagnetic.
This hammer is a ferromagnetic hammer.
Let's study a ferromagnetic solid. So this is iron, this is cobalt, this is nickel. All are the example of ferromagnetic substance. So in ferromagnetic substance, there are many atoms and their atoms contain electrons. Okay, so the electron is spinning, and because of that spinning the magnetic field is produced. So all the electrons present in that are aligned in different directions. So you can see here all the electrons, the spin is different, therefore their magnetic moment is different. Here so cobalt, same, all the atoms are randomly or you can say all the magnetic moment are randomly oriented, so there is a no net magnetic moment. Okay, so when the magnetic field is applied to such a ferromagnetic substance, so when unpaired electron is when a magnetic field is applied to the external magnetic field, all the unpaired electron in the metals and their compound aligned in the direction of the applied field. So what is the meaning of this? See, if I applied a magnetic field, so I am using a magnet and applying a magnetic field. As I applied a magnetic field, what will happen? all the magnetic moment will get aligned in the direction of the magnetic field. So see, all they have aligned. Now what will happen? Here you can see this arrow. What this arrow indicate? This is North Pole and this South Pole. So near this South Pole, there all are North Pole. Okay. So what will happen? The North Pole get attracted to the South Pole. So all the ferromagnetic substance will get attracted towards the magnetic field, and that is also strongly it is attracting. Okay. The ferromagnetic substance is that substance which are strongly attracted towards the magnetic field. And even the magnetic field is removed, then also this magnetic moment will not get randomly oriented. Okay, it will has a permanent magnetic dipole moment inside the ferromagnetic substance, and so ferromagnetic substance can retain the magnetism even after the removal of external magnetic field. So because of that, if such a substance is brought near any other substance, any ferromagnetic substance, that substance, this ferromagnetic substance will attract another substance. So it has a permanent magnetic dipole moment. Okay, and it is and such substance can be permanently magnetized also. Okay.
Example of ferromagnetic substance: gadolinium, iron hammer, cobalt hammer, chromium oxide hammer.
Solid state chapter ends here.